Couple of things. Number one, I want to kind of remind you of some stuff that's going on. So here's our Canvas page. And if you don't know, this is Sandus, my preceptor here, and this is her information. So if you can't get a hold of me, you can get a hold of her. Her office hours on Mondays and Wednesdays from 2 to 3 p.m. And Fretwell 321, I think that's the computer lab upstairs, so don't be surprised by that one. I'm going over here to the Hawk system because finally drop ad is over, so now things are going to start closing out on you guys and stuff. I also teach a Tuesday, Thursday class, so I'm trying to keep you guys synced up a little bit, but it's kind of difficult on Monday, Wednesday, Friday versus Tuesday, Thursday. But here's the deal. I extended the 1.5 section. It was supposed to be due last night. I decided to open up a little bit longer because, believe it or not, I still had people adding my class yesterday. It's kind of sad. So I give them the opportunity. So it's going to be closing this weekend, like on Sunday. That is the 1.5, 1.6A, 1.6B, and 1.8. All that stuff, all those lessons are going to be closing out. That's your homework sets and stuff that you have to certify on. You also have your first web test. That'll be due on Saturday, this Saturday. So go ahead. You got 2 attempts on this thing. So, and we'll take the highest grade on this guy. And it is what we call Quiz 1. It's pretty much on section 1.6 A and B. It's on section 1.6. Maybe a little bit of 1.8, but not much. It's basically on 1.6 is what these questions are coming from. And it's just making sure that you're keeping up and stuff. But this is going down as your quote-unquote your first web test. So every couple of sections or so, we'll give you a web test. We always make this stuff due on that Saturday. And just to make sure we make the lessons actually finish up being due on Sunday. But but we always give you that kind of a gap type thing here in terms of stuff. So the next one will be when I'm finishing it up today, which will be due next Saturday, which will be on chapter 2.1 A and B and stuff. So just want a heads up on that one. But before we get started on that stuff, I did have a question that I wanted to go over. This was a question posted to me, and finally I could see the problem, so now I can print it out. So here's my question right here, and this is one of your quiz questions, but I don't care if it's quiz or homework or whatever. If you don't understand something or other, I want to make sure you guys can do this thing. So here's my question. Let h of x be equal to the square root of x plus 11. You're supposed to find the function h of 5t plus 7, where t is greater than or equal to negative 18/5. All right, so here's the big deal on this stuff here. All we're supposed to really do is find h of 5t plus 7. This is that classic functional notation. I don't care what's in that parentheses behind that function. Whatever's in that parentheses is what I replaced x with in the original h of x problem. So since h of x is the square root of x plus 11, h of 5t plus 7 is going to be the square root of, plugging in for x 5t plus 7 plus 11. Now let's put a little parentheses right here. I'm really replacing the x with the 5t plus 7. But of course you want to clean this up. So this is equal to the square root of, there's 5t, and 7 plus 11 is 18. And honestly, this is your answer. You're done. It's the square root of 5t plus 18. Now, what probably throws people off is, what's this mess over here? T's got to be greater than or equal to negative 18/5. Well, they're just telling you what the domain is. And remember, it's just part of the problem, but the fact is this is a square root problem. And you can't take the square root of a negative number. You can only take the square root of 0 or positive numbers. So, if you're talking about the domain of this guy, what's underneath the radical, which is that 5t plus 18, must be greater than or equal to 0 for us to take the square root of it. And when you solve for t there, subtract 18, I get 5t is greater than or equal to negative 18, and divide by 5. This gives me that t is greater than or equal to that negative 18/5, and that's what they're referring to, that this is where this problem is actually defined at. Does that make sense? Questions? Remember, classic functional notation. I don't care what's inside the parentheses of this new function. If you have the original function h of x, you replace what's inside the parentheses, replace that x with it, and just clean them up, and that'll be your new function. Well, last time we were working on chapter 2.1 1A, we were doing left hand and right hand limits. Okay? So let's pick up where we left off here. And I am going to give you some major lecture stuff on this one, but what we were doing is we were basically doing what we call one-handed limits. Right side or left side limits. Left-handed or right-handed limits is what they're called. And so, and I gave you this big description of, okay, here's the deal. You got a function, and you're trying to figure out what's going on with this particular function. So, here's the big deal. So you get a big picture of it big time today. We're going to be taking the limit as x approaches some kind of number of a function. We're going to call that limit L. The idea behind this is this. You've got this function right here. We want to sit there and figure out what's going on with this function as x gets very, very close, as x approaches a. As x gets very, very close to a, what's going on with the function? Well, the reality is, it depends on the function. If the function doesn't have any problems at all, if this has no problems at all, what I mean by that is domain is all real numbers, you can chunk anything you want to in it. Here's the first rule of limits. If f of x has, quote, no problems. What's a problem? I can't divide by 0. What's a problem? Taking the square root of a negative number. You understand, these are mathematical problems. But if I have no problems on this thing, here's the rule. The limit as x approaches a of f of x is just going to be f of a. In English, that's just plug in a number. That is your first rule of limits. Plug in a number. If you get a number, you're done. That's the answer. Let me give you an example. Here's one. The limit as x approaches 2 of 3x squared plus 4. 3x squared plus 4 is a classic polynomial. Domain is all real numbers. You can chunk anything you want to in for x. So when I want to take the limit as x approaches 2 of 3x squared plus 4, that's going to be equal to 3 times 2 squared plus 4. 2 squared is 4. 3 times 4 is 12. Plus 4 is 16. Answer 16. Where I have a problem is something like this. And this is where we introduce the concept of the one-sided limit. If I want to take the limit as x approaches 2 from below of x squared minus 4 over x minus 2, you see this problem here. This has got a problem. X squared minus 4 divided by x minus 2. That divided by x minus 2, I have a problem when x is 0. Okay? And the only way I'm going to be able to analyze this particular problem is because I'll be dividing by 0. This is where you want to do your table in this quote-unquote incremental approach. Because 2 is my problem, and that's what I'm trying to take the limit as x approaches. As I get very, very close to 2, what's happening to this problem is what I want to know. This is when you do the table. This is your x and your y. Now, this idea of you're getting very, very close to 2, and you want to do it in stages. I mean, if you look at some of the charts, we start you out with 1, 2, and 1, and then we go to 1.5, 1.9. Basically, you go ahead and get close to 2. Now, that little minus sign means which side of 2 I'm going to go on. Because when you look at a number line, there are two sides of 2. Now, here's 1 and here's 3 up here. You can approach 2 from below, or you can approach 2 from above. When you approach 2 from below, that's that 2 from the minus side. When you approach 2 from above, that's that 2 from the plus side. So you're going after 2, but you got to know, quote, the direction that you're going after. We're going after from below. So I'm going after 2. Now, plugging in 1 in this thing is not going to give me any kind of major information. I want to get really, really close to 2. I'm going to plug in something like 1.9. Then I'm going to plug in 1.99. Then I want to plug in 1.999. I'm going to get close to 2. Go ahead and get your on your way, but you need to see this step. You don't just plug in a number and estimate what it is. You need to plug in at least 2 or 3 numbers on this thing to be able to catch a pattern. The key to this is patterns. So, here we go. 1.9. 1.9 squared minus 4 divided by parentheses 1.9 minus 2. and I get 3.9. Now I'm going to call this thing back down again, and now I'm going to plug in, and then 1.99. So I'm going to insert an extra little 9 into my numbers here. And I end up getting 3.99. And then I'm going to plug in 1.999. I think I caught the pattern, but you never know. One more show is we'll prove it if I actually have the pattern or not. If I plug in 1.999, I end up getting 3.999. So as this approaches 2 from below, what's this number approaching? 4. So my limit value, this thing is equal to 4. This is when you do the chart work, when you're actually taking the limit as you're going towards, quote unquote, a problem point. If you got a function that doesn't have a problem, first rule of limits, plug in a number, and you're done. Okay? This is the idea behind this particular problem. So, questions. So let's get back to what we were talking about last time. And we did a bunch of problems last time. So, and I'm going to pick it up over here. And we're going to start with problem number 5. Problem number 5 asks you this. Okay? This time we have a piecewise function. Given the function g of x is equal to 1/2 x, where 0 is less than x, which is less than or equal to 4, and x minus 1 for x is greater than 4, we want to complete the table. Basically, look at this problem. Where is my breaking point in terms of my piecewise function? Where do the two pieces of my function break at? What value? 4. 4 is my quote-unquote problem point, because if I'm less than or equal to 4, I plug in here. If I'm greater than 4, I plug in here. 4 is my breaking point. Does that make sense? And look at what they're asking. They're going to, this first one, take the limit as x approaches 4 from the left. So I'm going to write this properly. This will be the limit as x approaches 4. But notice they're plugging in numbers 3, 3.5, 3.9, 3.99, 3.999. They're approaching 4 from below 4 of your function, g of x. And I'm about to show you guys a trick real quick, but here we go. Since 4 from below, we're slightly less than 4, I'm going to plug into, when we're less than 4, that'll be the function 1/2 x. So, here we go. I'm just going to grab my handy-dandy calculator. They start me with 3. So 1/2 of 3 is, I can do that, 3.5, which for you math people is 1.5. I'm going to plug in 3.5. So that would be 1/2 times 3.5. I get 1.75. I plug in 3.9. That'll be 1/2 times 3.9. I get 1.95. Now I'm going to plug in 3.99. 1/2 times 3.99 is 1.995. Now I'm going to plug in 3.999. 1/2 times 3.999, I'm going to get 1.9995. So, as this approaches 4 from below, what is my value of my function approaching? What is the limit? 2. And it's coming from below, true, but we just give you the number. It's 2. So the answer is 2. But now, they want me to take the limit as x approaches 4, but this time from the right. That'll be from the plus side of g of x. Okay? And so when I take the limit as x approaches 4 from the right side, that means we're slightly bigger than 4. And when we're bigger than 4, we plug into the piecewise part of the function x minus 1. So they're going to start me out with 4.5 here. So I can do this math without a calculator. 4.5 minus 1 is 3.5. Then they asked me to plug in 4.1. 4.1 minus 1 is 3.1. 4.01 minus 1 is 3.01. 4.001 minus 1 is 3.001. And 4.0001 is going to be, minus 1 is going to be 3.0001. So as this approaches 4 from above, what number is this approaching? 3. Therefore, the limit is equal to 3. Does that make sense? So the limit as x approaches 4 from below was 2, and the limit as x approaches 4 from above is 3. But I want to show you guys something, rather. I didn't have to do a chart. Let me show you. They did a chart on this one, and there's certain problems I'm going to have to do a chart on, but this one isn't one of them. And the reason for that is this. Here's the question. Take the limit as x approaches 4 from below of g of x. Well, with a piecewise function, you've got to identify the piece that you're going to plug into. Since we're taking the limit as x approaches 4 from below, we're below 4. Which piece of my piecewise function do I use? The top function or the bottom function? Less than 4. The top function, 1/2 x. So this is equal to the same thing as the limit as x approaches 4 from below of 1/2 times x. Now, look at this as a standard limit problem. Take the limit as x approaches 4 from below of 1/2 x. 1/2 x doesn't have a problem. You can chunk any number you want to in 1/2 x. What number are we going to plug in? Because that's the first rule of limits, is plug in a number. You're going to plug in 4 because that's what we're going after. So this will be 1/2 of 4. What's half of 4? 2. And you get your answer. You didn't have to do all this stuff. Does that make sense? Same idea on the next one. I'm going to take the limit as x approaches 4 from above of g of x. 4 from above, 4 from the right, means I'm plugging in numbers slightly bigger than 4. Based upon my piecewise function, if I'm bigger than 4, the function is x minus 1. So this will be equal to the limit as x approaches 4 of x minus 1. First rule of limits is plug it in. 4 minus 1 is 3. And I get my answers. But we'll get you into this idea. Now, this is a definition thing. That incremental approach. I'm going to get very, very close to 4, either from below or from above, and we're trying to see where the function's going after. But there's going to be some shortcut methods on this stuff. First rule of limits is plug in a number. If you don't have a problem, you'll get the answer every time. Now, let me do another example here. Now, first off, I can do this problem here. And let's take a look at number 6. Let me blow this up for you guys in the back there. If p is a polynomial function and a is a real number, then the limit as x approaches a from below or from the right left of p of x is equal to what? And the limit as x approaches a from the right of p of x. Now, what they're referring to here is a polynomial function. A polynomial function is a function that looks like, you remember the old polynomials? A polynomial would be y equals your b sub n, x to the n, plus b n minus 1, whatever b happens to be, x to the n minus 1, plus dot dot dot, plus b1x, plus b0. That is what a polynomial looks like. The big deal about a polynomial is its domain. The domain is all real numbers. That's negative infinity to infinity. You can plug anything into a polynomial and you can get an answer out of it. And because the domain is all real numbers, polynomials don't have problems. So this is what they're saying. If you're trying to take the limit as x approaches a from below of this p of x, what's the first rule of limits? Plug it in. And I plug it in, I'm going to get p of a. Okay? And that's the answer for this one. P of a. On this one, when I take the limit as x approaches a from the right of p of x, first rule of limits is plug it in. P of a, I'm going to get p of a. That's the answer. First rule of limits is plug it in. You get p of a. But now, sometimes you have a problem. Let me give you another example of a problem here. I want you to take the limit as x approaches 2 of 5x plus 1 over x minus 2. This one has a problem. Okay? It's 5x plus 1 divided by x minus 2. And I'm going to make you take the limit as x approaches 2 from below. Because, first off, my problem is 2, and that's what we're going after. Does that make sense? I'm dividing by 0 when I plug in 2. First rule of limits, plug it in. The problem is, when I plug it in, I'm going to divide by 0. Which means, when I divide by 0, or I have a problem, take the square root of a negative, or whatever the case may be, I've got to do this little t-bar thing. I'm going to sit there and plug numbers into it. And so here's x, and here's y, and look what happens. I'm going to get close to 2. from below. What numbers are slightly less than 2? What kind of numbers am I plugging in? 1.9, 1.99, 1.999. These are numbers are close to 2, but slightly less than 2. Okay, so plug this thing in. This would be, parentheses random numerator, 5 times 1.9 plus 1 divided by parentheses 1.9 minus 2. I get a negative 105. Now I'm going to change it and plug in 1.99. When I plug it in, I get negative 1,095. I plug in 1.999 into these numbers. So insert another 9 here. Plugging in 1.999, I get negative 10,995. So as this number approaches 2 from below, what is this number approaching? Is it going towards a particular number? I'm going from 105 to 1,095 to 10,995. What happens to my numbers? Well, granted, and keep multiplying by 10, and what you're going to get? Careful. There's two types of infinity. There's blowing up, that means you're going up to positive infinity, and there's blowing down, which means you're going down to negative infinity. Which one are we going towards? The answer is negative infinity. So you can get negative infinities on these answers. Does that make sense? It didn't go to a single number. If it doesn't go to a single number, if it continues to blow up, we say it blows up to positive infinity. If it blows down, we say it blows down to negative infinity. So you can get infinity for answers on this stuff because you're not actually going towards a single number. And so you get the idea, the same idea here. When I take the limit as x approaches 2 from the right side, 5x plus 1 over x minus 2. Same idea here. But 2 from the right, I'm going to plug in numbers like 2.1, 2.01, and 2.001. Because I'm trying to catch a pattern, so you've got to plug in several numbers here. So this will be 5 times 2.1, parentheses around this for a guy, insert that parentheses. 5 times 2.1 plus 1 divided by 2.1 minus 2, and I get 115. Now I'm going to plug in 2.01 into my function. So I'm using the famous recall button down there and just inserting some zeros. I get 1,105. And now, that my 10 power thing here, when I put in 0, I bet it's going to be something like 11,000 or something or other. So insert that 0, and what do I get? Yep, 11,005. So in this particular problem, as I approach 2 from above, what number is this guy approaching? This would be positive infinity. This would be decreasing. This would be increasing. It continuously decreases, you get negative infinity. Continuously increases, you get positive infinity. So I'll put it up here so you can take a picture of it. Because you guys are just sad in the ability to take notes. All right, so here we go. Take a look at number 7 up here. It says this. If f of x increases without bound as x approaches a from the left or from the right, we say f of x approaches what? You're going to increases without bound. What is your definition of increase without bound? Keeps going up. And the answer is positive infinity. But part B, if f of x decreases without bound, as x approaches a from the left or from the right, we say that f of x approaches negative infinity. Decreasing without bound, that means you go down, you go to negative infinity. Increasing without bound, that means you blow up, you go to positive infinity. So just a symbolism here, infinity, negative. Does that make sense? Okay? So, if you go and watch, go to www.hawkstv.com. They do a couple of examples on section 2.1a. This little video for you guys. And this is a similar problem. It's not the exact same problem. This is a similar problem. First one, take a look at this guy. We want to take the limit as x approaches a I'm sorry, x approaches 1 from below of x minus 2 divided by x minus 1. Now, when I look at this problem, I look at where I'm going after 1 from below. I look at my function, x minus 2 over x minus 1. That divided by x minus 1 means when I plug in 1, I'm going to divide by 0. That's a problem. Because this guy has a problem, I'm going to do the chart. When to do the chart and when not to do the chart. So here we go. Plug in numbers very, very close to 1 that are slightly less than 1. Slightly less than 1 would be like 0.9, 0.99, and 0.999. Notice I always plug in about 3 numbers. Close, closer, and even closer because I'm looking for a pattern. So here we go. Clean up this guy and start the calculator all over again. Parentheses, 0.9 minus 2 divided by 0.9 minus 1. When I plug it in, I get 11. Now I'm going to plug in 0.99. I get 101. And now I'm going to plug in 0.999. And I get 1001. So as we approach 1 from below, what is my limit value approaching? Positive infinity. So the answer we would say would be infinity. Typically we write infinity, but we would not take off points if you put plus infinity on this thing. That's fine. But positive infinity is our definition of infinity. Does that make sense? Look at the next one. Find the limit as x approaches 2 from the right of x squared plus 4x minus 2. First off, where's my point? It's at 2. Look at your function. It's x squared plus 4x minus 2. This is a polynomial. This polynomial, x squared plus 4x minus 2, doesn't have any problems. I'm not dividing by anybody. I'm not taking square root of anybody. It's a classic polynomial. And the domain of a polynomial is all real numbers, which means I can plug anything into this thing I want to. First rule of limits. Plug it in. So this would be equal to, we're going after 2, that'll be 2 squared plus 4 times 2 minus 2. 2 squared is 4. 4 times 2 is 8 minus 2. 8 minus 2 is 6 plus 4 is 10. The answer is 10. First rule of limits. Plug it in. I didn't do a chart. I didn't take my time to plug in all these numbers and everything. If you don't have a problem, first rule of limits, plug it in. And if you get a number, you're done. Answer is 10. Does that make sense? And it wouldn't matter if I went from the left side or the right side. The function has no problem. Just plug in the number. Does that make sense? All right? So let's take a look at some of these practice problems here. Take the limit as x approaches 5 from below of x minus 9 divided by x minus 5. Well, this one has a problem. Where's my problem point at? 5, and that happens to be the number we're going after for the limit. So this is a problem where I would want to do a chart. So x and y, we're going after 5. What side of 5 are we going after? From below. So what kind of numbers are below 5 that I want to plug in? 4.9. 4.99, 4.999. So here we go. Parentheses around your numerator. 4.9 minus 9 divided by 4.9 minus 5. And I get 41. 4.99. Plugging in 4.99 for my x's here. 4.99 minus 5 divided by 4.99 minus 5, I get 401. Next one's probably going to be 4001. Let's find out. Now I'm going to plug in 4.999, so insert another 9 into this thing. And I get, 4001. So, as we approach 5 from below, what's my limiting value going towards? Infinity, aka the answer is positive infinity. And again, you can just throw an infinity and Hawk system will know that it's positive infinity. You, with a negative infinity, you gotta put the minus in front. Okay? Same idea on this one. Take the limit as x approaches 0 from below of x plus 46 divided by x. Well, this guy has a problem. We're dividing by x. And when x is equal to 0, we have a problem because I can't divide by 0. And that happens to be the number we're going after. So this is another example of when I would want to do my t-bar, plug in numbers. But I got a question for you. What kind of numbers am I going to plug in? I'm going after 0 from below. So here's my number line, and here's 0 right here. And here's -1, and here's +1. If I'm going after 0 from below, I got to plug in numbers on the negative side. But I want numbers very, very close to 0 that are negative. What's a number close to 0? 0.1, that's close to 0, but on the left side, we want it to be negative. So I'm going to plug in numbers like -0.1, -0.01, and -0.001. Does that make sense? So here we go. Parentheses random numerator, -0.1 plus 46 divided by -0.1. And I get -459. Now I want to plug in -0.01, so insert another 0 on this mess. And I get -0.01 plus 46 divided by -0.01, which is -4,599. Yep, I pretty much can catch the pattern now. It seems to be blowing down. But let's just double check it one more time. I'm looking for patterns. -0.001 plus 46 divided by -0.001. And I get, yep, -45,999. Pretty much, as we approach 0 from below, my limiting value is approaching negative infinity. This answer is going to be negative. Does that make sense? All right. Take a look at this guy. Take the limit as x approaches 9 from the right of x cubed minus 81x squared plus 729x minus 729 divided by x minus 9. That divided by x minus 9, and we're going after 9, means I'm going taking the limit as I go to a problem. That tells me how to use my t-chart. And I want to go from 9 from above. Slightly bigger than 9, I'm going to plug in numbers like 9.1, 9.01, and 9.001. If you're confused about the numbers you should plug in, well, draw yourself a number line, write down 9, and you're approaching from above, so you can actually see what kind of numbers you can plug in. 9, slightly bigger than that, that's where your 9.1 type stuff comes. Okay? So now, this is a great example. Look at this guy. Now my problems are getting a little bit larger. All right? They're getting a little bit larger. Look at these guys. X cubed minus 81x squared plus 729x minus 729. Well, I taught you guys last time there's a couple of different ways you can do this problem. Now, when they're small functions, I just use to type them in on the home screen here. But now my functions are getting kind of large. And I don't want to keep typing this thing in because I'm going to be plugging in 9.1 into lots of things on this guy. So I'm going to use the graph mode is the faster way of doing stuff. So I'm going to go up here and clear out the old function there. Put a parenthesis around your numerator. X cubed minus 81 x squared plus 729x minus 729, close parentheses, divided by parentheses, x minus 9. Now, the number we're approaching is 9. When I do a zoom 6, a zoom standard, I don't care where the graph is at, but it's going to graph between -10 and +10, -10 and +10. All I care about is the x numbers, -10 to +10. The number I'm going to plug in has got to be inside this range. Otherwise, I have to hit the window and kind of change my range to something else. So if I was going after 11, I would have to change the range because this goes from -10 to +10, and it doesn't graph anything after +10. If I want 11, I'm going to have to extend this and change this like 12 or 13 so I can see it. But 9 is in between -10 and +10. So I don't care where the graph is at. I'm going to do second, calculate, and do the value. What number are we plugging in for x? First one's going to be 9.1. When I plug it in, I get Hold on a second, let me double check my function here. X cubed minus 81x squared plus 729x minus 729 divided by x minus 9. Let's see what we got here. Just double check. Yeah, okay. I'm going to make sure I typed it in right. So when I did that, second calculate value, everything's right, negative 1.9. I get negative 491.39. Okay, now I'm going to plug in. And once you're in that second calculate value mode, you can just keep plugging the numbers. 9.01. I get negative 486.5399. And now I want to plug in 9.001. And I'm going to get negative 486.05. I got a question for you. Can you tell what number we're approaching? Now, this thing's not seem to be blowing down to negative infinity because the decimal seems to be in the same spot. I got negative 491, negative 486, negative 486, and a smaller decimal here. If you're not sure, get even closer. Plug in one more number. How about 9.000001? I mean, get really darn close to this thing. So 9.00000, that's 5001. What do I get? Negative 486.00001. So as this approaches 9, what number is this guy approaching? Negative 486. Very good. So the limit of this guy, so we are actually going to a number, the answer is negative 486. Does that make sense? And my point is, sometimes it's hard to tell, then get even closer. Okay? Now, here comes a classic piecewise function. I showed you guys the trick on this one before. G of x is equal to negative 81x minus 7 if x is less than negative 1, negative 5x cubed plus 3 if x is greater than or equal to negative 1. You're supposed to take the limit as x approaches negative 1 from below of g of x. Well, that's going to be equal to the limit as x approaches negative 1 from below. From below means we're slightly less than negative 1. Since we're slightly less than negative 1, which piece of my piecewise function do I use, top or bottom? We're going to use the top one. X is less than negative 1, so I'm going to plug it into the negative 9x minus 7. Now, you can do the chart if you want to, but here's the rule. This is the piece I'll be plugging into, and look at it. It's negative 8x minus 7. Does negative 8x minus 7 have any problems? No. So when it doesn't have a problem, first rule of limits is plug in the number. So this would be negative 8 times, x is going towards negative 1, minus 7. Negative 8 times negative 7 is like 8, minus 7 is 1. The answer is 1 to this one. Now, take the limit as x approaches negative 1 from the right. That means we're slightly bigger than negative 1. So this would be equal to the limit as x approaches negative 1 from the right. Bigger than negative 1, I plug into the greater than negative 1, I plug into the bottom piecewise function. Negative 5x cubed plus 3. First rule of limits is to do what? Because once again, negative 5x cubed plus 3 doesn't have any problems. Plug it in. So this will be equal to negative 5 times negative 1 cubed, plugging in negative 1, plus 3. Negative 1 cubed is negative 1. Negative 5 times negative 1 plus 3. Negative 5 times negative 1 is 5, plus 3 is 8. Answer's 8. Now, in that same context, look at number 5. F of x is equal to another piecewise function. X squared minus 1 if x is less than or equal to 5, and 1 over x minus 5 if x is greater than 5. My breaking point is 5, and yep, what a surprise. They want me to take the limit as x approaches 5 from below f of x, and then take the limit as x approaches 5 from above of f of x. If I'm taking the limit as x approaches 5 from below, that means I'm slightly less than negative 5. So this is equal to the limit as x approaches 5 from below. 5 from below, 5 from below means I'm slightly less than 5, and I'm less than 5 means I plug into the top function, x squared minus 1. Look at that guy, x squared minus 1. Does that guy have any problems? No. First rule of limits is plug in the number then. Since this has no problems, you plug in the number. 5 squared minus 1 That's 25 minus 1. The answer is 24. Does that make sense? But now, take a look at my next guy. Take the limit as x approaches 5 from the right. That means I'm going to take the limit as x approaches 5 from the right of this f of x, but from the right, that means I'm slightly bigger than 5. Bigger than 5, the function is 1 over x minus 5. 1 over x minus 5 has a problem. Where is this guy's problem at? At 5, when the denominator equals 0, which is at 5, and that's the limit that we're approaching. So because this guy has a problem, I'm going to have to do the chart method on this part. Does that make sense? And I'm going after 5, slightly bigger than 5. So I'm going to plug in numbers like 5.1, 5.01, and 5.001. This is a small function, so I'm just going to plug it on my calculator. 1 divided by, parentheses, 5.1 minus 5 is 10. Plugging in 5.01, inserting a note. 1 divided by 5.01 minus 5 is 100. Take a wild guess what the next one's going to be. Yeah, pretty much, but let's double check it. 1 divided by 5.001 minus 5 is, you nailed it, it's 1,000. So, as we approach 5 from above, my limiting value, 10, 100,000, where we're going? We're increasing without bound, aka it's going towards infinity. The answer for this one is positive infinity. Does that make sense? All right, there's 2.1. A. Section 2.1b. Section 2.1b is basically on what we call full limits. So the last section was called left side and right side limits, left hand and right hand limits. We're approaching it from either side. This is called a full limit or limit. Okay? So now we're talking about, and I'm actually trying to introduce this idea of basically a limit as straight up as a function here. So here's the deal. This is called a full limit. See, these guys are one-side limit. For a function and a real number t, if you take the limit as x approaches whatever t is from below of f of x equals L, and the limit as x approaches t from the right of f of x equals the same L, where L is a real number, then we say the limit as x approaches whatever t is of f of x is actually equal to L. This is called a full limit. Let me give you the basic definition of this guy. Okay, it's a visual thing. See, a limit is where you're going. So if I take the limit from below, that's this finger point, this is the limit from above, whatever number I'm going after. If they go towards the same number, then we say the full limit is equal to that number. The full limit is a limit as x approaches whatever number without the little plus or minus behind it. This doesn't have a little plus or minus behind it. So you're going after from both sides. They've got to go to the same number. If you ever have this, the limit from below goes here, limit from above goes here, and if they're not going to the same point, we say the limit does not exist. Okay? So, we say the limit of a function f as x approaches a real number t blank if and only if t approaches x approaches t of f of x equals L, where L is the real number. See, this thing exists. You actually get an answer when you actually have a full limit. The limit from below is equal to the limit from above. This thing's going to exist. If they're not equal to each other, this is what I was just talking about. If the limit as x approaches t from below of f of x does not equal the limit as x approaches t from above, you got this situation. Then we say the limit as x approaches t of f of x does not exist. My famous D&E. Does that make sense? Limit does, that's an either, does not exist. The definition, and I'm telling you a bunch of stuff, but you need to get in your notes, is this. The way we define a limit is you got to take the limit as x approaches some amount of number of f of x, and it's got to equal L. And L, listen up, has to be a real number for the limit to exist. The limit from below has to go to a number, the limit from above has to go to the same number, then we say the full limit exists. If you have this situation, the limit from below goes to one number, limit from above goes to a different number, the full limit doesn't exist. And if you got a limit blowing up on you, and the other side blowing down or even blowing up, if you ever get an infinity answer on this stuff, the limit as x approaches t of f of x equals either plus or minus infinity, then we say the limit as x approaches t does not exist. That famous D&E. Why? Because for a limit to exist, our definition is it's got to go to a single number. Infinity is not a number. It's an idea. It's getting bigger and bigger and bigger, or negatively, smaller and smaller and smaller. You're not actually going towards a number. For a limit to exist, you got to approach a number. So when you got a limit on one side or the other blowing up or blowing down, increasing without bound, or whatever the case may be, then we say the limit does not exist. We're talking about that full limit here. Number 5. If any limit problem, if the numerator has a limit different from 0, and if the limit of the denominator is 0, then the limit of the quotient must fail to exist. Why? All right, let me read you in the code here. It says this. You're taking a limit as x approaches whatever number of f of x. And what you got here is we got a fraction. This is some kind of number that's not 0. Not 0. Divided by the denominator is 0. Have you noticed every time we started dividing by 0, we did the little incremental approach, you were either blowing up to infinity or blowing down to negative infinity was my answer. But what do we say if the limit is either positive infinity or negative infinity? What about the limit? It does not exist. Fail to exist. Does not exist. However you want to write that. Does that make sense? A number divided by 0 doesn't exist. But there's a special case. Okay? And that's the next one. Okay, that one. If both the separate limits of the numerator and the denominator are 0, there may be a limit for the quotient. No guarantees, but there may be a limit for the function. And let me explain. If I take the limit as x approaches t of some kind of weird function here, and I get 0 divided by 0, what is 0 divided by 0? Now, you're right. Officially, it should not exist because I'm not allowed to divide by 0. But wait, we're talking about math here. Shouldn't 0 divided by 0 cancel and the answer be 1? I mean, 5 divided by 5 cancels, and that's 1. 7 divided by 7 cancels, that's 1. 0.1 divided by 0.1 is 1. It cancels. As I get very, very close to 0, that sucker's going to start canceling. But the denominator is 0. And when the denominator is 0, it's not supposed to have an answer. Does not exist. Blows off to infinity. Wait a minute. The numerator is 0. What's 0 times anybody? 0. What's 0 divided by anybody? 0. So is the answer 0? Is the answer does not exist? Is the answer 1 because it cancels? Yes. Sometimes it works each one of those things. We call this case indeterminate. 0 over 0, that's going to be your very special case when it comes to calculus, because you're going to get 3 different kinds of answers. You can get 0, you can get infinity or negative infinity, does not exist stuff here, or you can get a number because the zeros cancel. That's indeterminate, and that's the kind of stuff we're going to be focusing on. So that's when we say it may have a limit. It may or may not. A limit expression of the type, limit as x approaches a of g of x over f of x, is called an, that was the word I was using, indeterminate form of type 0 over 0 if the limit as x approaches a of g of x is 0 and the limit as x approaches a of f of x equals 0. The top and the bottom both have to go to 0. 0 divided by 0, that is that indeterminate form. Okay? Now, what we're going to be doing in this section when it comes to indeterminate forms is this. First rule of limits, plug in a number. If you get a number, you're done. Second rule of limit, plug in a number. And if you get a number divided by 0, that does not exist. I'll give you cases here. Give me a D and E on the whole problem. Let's go to the next problem. Number divided by 0. Third and most important case. If you take the limit as x approaches a of some number and you get 0 divided by 0, you are supposed to, quote unquote, quote me out here, do algebra. Clean it up. Something is going to clean up nicely here, hopefully. And then redo the limit stuff. Clean it up. So there's some algebra to be had here. And that's what we're saying here. A strategy of solving a problem that is in the indeterminate form of 0 over 0 is given by a two-step method. Replace the quotient and simplify the expression after factoring. And 2, evaluate the new limit problem by substitution. Plug it in is my definition of substitution here. And to the denominator, if the denominator does not have a limit of 0 as x approaches a. This is what I'm saying, do algebra. Okay? So, I got 1 minute. Wait, I can do one more problem. All right, so, take a look at this guy right here. Take the limit as x approaches -5 of x plus 5 divided by -4x squared plus 100. What's the first rule of limits? Always. Plug it in. If I plug it in, I'm going to get -5 plus 5 over -4 times 5 squared plus 100. 5 plus 5 is 0. 5 squared is 25 times -4 is -100 plus 100 is 0. It's a famous 0 over 0 case. So what you're going to do here is clean it up. This will be the limit as x approaches -5, of x plus 5 divided by, I'm going to clean this up, I'm going to write this as -100 minus 4x squared. I just put the negative guy in the back. Watch this. I'm going to clean this guy up. This is equal to the limit as x approaches -5 of x plus 5. There's not much I can do with that guy, but 100 minus 4x squared. First thing you can do is you can actually factor out, I can actually factor out a -4. Let's do that. Factor out a -4, that leaves me with a positive x squared minus 20. Is it, no, let's see here. 425. I can do math. 425. Does that make sense? Now, all I did was factor out a -4 here. Wait a minute, I'm not done yet. Keep factoring. Limit as x approaches -5 of x plus 5 divided by -4. How does x squared minus 25 factor? That's one of these guys you're supposed to know from old college algebra. It's a, quote, difference of squares. How does the difference of squares factor? X plus 5 times x minus 5. And what happens in terms of cleaning it up? What do you see? The x minus 5s are going to cancel. And you're left with the limit as x approaches -5 of 1 over -4 times x minus 5. And after you cancel, first rule of limits, plug in the number again. So this will be equal to, plug in the number, I don't write limit anymore, that'll be 1 over -4 times -5 minus 5. 1 over -4 times, what's minus 5 minus 5? Minus 10. What is -4 times -10? 40. What's the answer? 1 over 40. This is the idea of the algebra with limits, and this is a full limit of cleaning it up. But first, I checked it out. If I got 0 over 0, I'm going to, quote, do algebra. And that algebra that they're focusing on is this idea of factoring and canceling. With that 0 over 0, something should cancel. We'll do more of these problems next time. Don't forget, Monday's a holiday, so I'll see you guys back on Wednesday. You got homework to do. Make sure you do all your lesson homework that's closing out on you guys and your first quiz. That's due on Saturday. See you guys then.